Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back in General Chemistry lecture. Inshallah, today we are going to discuss together chapter 10, which concerning the properties of gases. Bismillah. Chapter 10, gases, properties of gases. Inshallah, this will be done by me, Mahmoud Abdel-Latif, under the Chemistry Department, College of Science, United Arab Emirates University. Inshallah, I'm going to cover in that chapter the following items, and before that, just look to this figure in the right hand side. If you have a balloon, okay, with it contains a gas, wherever the gas could be a mixture of gases like air, so to say. And if you try to heat this kind of gases, you will find that the volume of the balloon increases, okay, and if you try to cool it, the volume decreases, and so on. Okay, inshallah, I'm going to cover the characteristic of gases, and we will define pressure and know what's the units of pressure that can be used to measure the pressure. And then we will go to gas laws, which some mathematical expression which govern the properties of gases, and then we will derive the ideal gas equation and the ideal gas law, and we will see how we can use the ideal gas equation for the application in the chemistry, calculation the density, calculation the molar mass, and so on. And inshallah, today lectures I'm going to end up with the Dalton's law, which concerns the partial pressure of mixture of gases together. Let us start. Okay, before we start, we have discussed in chapter 1 the matter, and we found that the matter can be divided into 3 subcategories according to the physical status, into liquid and solid and the gases. Okay, and just reminding you that solids has a definite shape and a definite volume, and liquid has a definite volume and indefinite shape, while gases have indefinite volume and indefinite shape, and solid cannot be compressed, gas is highly compressible, and so on. So gases, its characteristic of gas, it expands to fill their containers. Okay, it takes the shape of the container. If you put it in a conical flask, it takes the shape of the conical flask. If you put it in a cylinder, it takes the shape of the cylinder, and so on. Gases are highly compressible. It can be compressed, okay, have extremely low density. The density of the gas is very, very low comparing to liquid substances and solid substances, okay, and so on. Actually, gases are highly compressible. It can be compressed and occupy the full volume of their container. As I mentioned, if you put it in a cylinder, it takes cylinder. In a bowl, the shape of the bowl. A conical flask, it takes any glassware, it takes its shape. Okay, when gases are subjected to pressure, okay, its volume decreases. Okay, if you compress, say to say, a balloon, for example, you will find that its volume decreases. There is a inverse relationship between the pressure and the volume. Inshallah, we're going to discuss it in details in the first gas law, which is Boyle's law. Okay, gases are always form a homogeneous mixture. What does it mean? Okay, we have discussed before the mixture could be homogeneous and heterogeneous. Okay, but when we are talking about gases, there is no any heterogeneous mixture of gases. All the gas mixtures are homogeneous. Like the most common example, air, which contains oxygen, hydrogen, nitrogen, and so on. Okay, gases only occupy about 0.1% of the volume of their container. okay, if you have a container, so to say like this one, and it's filled by gas, the real volume of gas is just only 0.1%. It's a very, very small ratio. Okay, this table showed you some gases at room temperature, some common compounds that are gases at room temperature. For example, this is, we have discussed before how to name the acids. It could be hydrocyanic acid or hydrogen cyanide, okay, hydrosulfuric acid, if you name it as an acid, or hydrogen sulfide, carbon monoxide, carbon dioxide, methane, ethane, propane, okay, nitrous oxide or dinitrogen monoxide, it's okay, or nitrogen dioxide, ammonia, and sulfur dioxide. All these compounds are gas at room temperature. Just I would like you to just concern, for example, these two gases, carbon monoxide and carbon dioxide. The only difference between both is just only one oxygen atom, but actually they are highly different in properties. This one, it's a very, very toxic, it's poisonous, okay? Okay, while carbon dioxide, we use it in the soft drink, okay, like cola, Pepsi, and so on, okay, and so on. Okay, once we are talking about gas, we have to talk about some parameters. The most important parameters you can explain the behavior of gases are, the parameters. It could be, there are 3 or 4 parameters, very, very important when you are talking about gas. The first one is volume, okay, and it represented by V, and second one pressure, okay, and presented by P, and third one temperature, and represented by T, it's by Kelvin, temperature in Kelvin, okay, temperature in Kelvin, and the last one, parameter which is important, the amount of gas, which is, you can represent it by N, which is number of moles, okay. Just reminding you that pressure is defined as force per unit area, okay, force per unit area, and the force is measured by Newton, and the area measured by meter square, so to say. So one could expect that 1 unit of the pressure units is Newton divided by square meter, okay. The force, according to second Newton's second law, or second Newton's law, is given by mg, where m is the mass and g is the acceleration of gravity. Okay, and the unit of force is Newton. Okay, mg, it's weight, which is, okay, mg, it's weight. So the pressure, okay, the Earth has, the planet Earth, it's a characteristic, or one of its most important feature of the Earth. It has an atmosphere which surrounds the Earth, and okay, actually this atmosphere, the weight of that atmosphere, the mixture of gas exerts a pressure on the surface of the Earth, okay. As I mentioned, the pressure is the force, which is weight per unit area, okay. So if we measure the weight of a column of the atmosphere, and per unit area, per unit square area, 1 meter, the weight of this atmosphere, it's a pressure, or the weight of the atmosphere exerts a pressure which is given by atmospheric pressure, which is the weight of that column of the mixture of gas. So pressure is the amount of force applied to an area, and this is mathematical expression for the pressure. The atmospheric pressure due to the atmosphere is the weight of air, as I mentioned, per unit area, okay, per unit area. Okay, to be a good chemist and a good physicist, you should be very aware with the units of the parameter you are dealing with. Pressure, there are many units can be used to measure the pressure. Okay, according to the its loads, force per unit area. So it should be unit of force divided by unit by area, which is Newton per square meter, and this unit is known by Pascal. Okay, barometric pressure. Barometric comes from the barometer, which the instrument which we use to measure the atmospheric pressure. One bar equals to 10 to the power 5 Pascal, or you could write 100 kilopascal. Okay, there are different units for the pressure, and it's highly used. Important. The first one is torr, and second one millimeter mercury, and both of them are equal. These are one torr equal to millimeter mercury, and the most common one is the atmosphere. Okay, atmosphere. Okay. Actually, one atmosphere. Okay, one atmosphere equals to 760 millimeter mercury, which in the same time equals to 760 torr. As I mentioned, they are the same, and you could convert millimeter to centimeter. Okay, just divide by 10, it should be 6 centimeter mercury. Okay, these are units of the pressure, and we are going to deal with during this chapter and in the exams and so on. Okay, how we can measure the atmospheric pressure? We can measure it with the barometer, and the barometer is something like this one. Okay, just you get a capillary tube and fill it with mercury, and just immerse it in a container, glassware which you contain mercury. You will find that the mercury will rise in that capillary tube with a certain height h, which exactly 76 centimeter, okay, or 760 millimeter. It's okay, the same both. Okay, and actually the pressure at equatorial point, okay, or the points in the same plane are equivalent. The pressure at that point should be equal to the pressure at that point. Okay, and the pressure at that one, actually it's atmospheric pressure. Okay, it's the weight of the column of the air of the atmosphere. It's atmospheric pressure exerted by atmosphere on Ch10 surface. Okay, while the pressure at that point equals to the weight of this column of mercury, which its height, this one or this one. Here it's a vacuum. Okay, above the mercury it's a vacuum, above it it's vacuum. Okay, so pressure exerted by Hg column, mercury column, and Hg surface. So we can conclude that the atmospheric pressure is the weight of that column of mercury. Okay, which exactly is this one, 762 or 760 millimeter mercury. That's great. Okay, that's very great. Okay, second one, if you have a gas and you would like to measure its pressure, how you can measure the pressure of a certain gas? You can measure the pressure of any gas by manometer. It's an instrument which can be used to measure the pressure of any gas. It looks like that figure exactly. It's something like, okay, a glassware or cylinder, so to say, which containing the gas, okay, with a valve here, and it will be connected with the U-tube, okay, U-shaped tube, okay, which contains the mercury, and without any connection with the cylinder, the surface of the two arms of the U-tube should be the same, okay, and if you connect one end of the tube with the cylinder which containing the gas, Okay, this gas will exert a pressure on the surface of the mercury, so it will decrease the height of the mercury in this arm and increasing the height of the mercury on the other arm. Okay, at that point, the pressure, it should be the pressure of that gas we are which under consideration. Okay, which equal the pressure at the same point in the other arm. Okay, pressure here it's equal to pressure here. So the pressure at that point, it should be equal to the height or the weight of the column of height h plus the atmospheric pressure, okay? So the pressure of the unknown gas is given by that equation equal to the atmospheric pressure plus pressure due to the weight of the column of mercury of height h, which is, okay, pH, it's equal to rho gh, okay, where h is the height and rho the density and the gravitational acceleration, and so on. So the manometer is used to measure the difference in pressure between atmospheric pressure and that of a gas in a vessel. Okay, that's great. Okay, let us define a new concept, which is standard pressure. Standard pressure. What does it mean, standard pressure? I'm sure all of you have heard that the pressure is measured at the sea level. Okay, at the sea level, it's called the standard pressure at a certain temperature. Okay, normal atmospheric pressure at sea level, okay, is referred to standard pressure. Okay, we're going to define later on standard condition, which is called STP. Okay, it's something different, but standard pressure here, it's the pressure at the sea level. It's the pressure at the sea level and equals to 1 atmosphere, okay, which equals to 762, in the same time equal to 760 millimeter mercury, in the same time equal to 76 centimeter mercury, okay, in the same time equal to 100 kilopascal, and so on. It's called the standard pressure. Okay, now let us discuss the gas laws, and you are going to start with Boyle's law, which studies the relation between volume and pressure. Okay, actually there are inversely proportionality between the volume and the pressure of a gas, where, okay, the volume is inversely proportional to the pressure. When you are discussing, okay, studying or explaining or discussing two parameters, okay, we concern the other parameter as fixed. So the amount of gas and temperature of gas should be constant. Okay, great. So the volume of a fixed quantity N of a gas at constant temperature T in Kelvin, okay, is inversely proportional to the pressure. Okay. This figure illustrating that law. Okay, if you have a U-shaped like that one, and you have a gas here, its volume is 60 milliliter, okay, and the pressure at that point equal to the pressure at that point. At that point equal to the atmosphere, okay, it's open arm, okay. So the pressure of that gas, or this amount of gas, it's 1 atmosphere. That's great. If you decrease this volume to half, instead of 60, becomes 30. Okay, according to that relation, okay, this one you can replace this proportionality constant with equal sign. It should be constant times pressure. So what does it mean? You could write V1 divided by P1 equals, so constant should be V2 P2. So, okay, if you substitute by volume 60 here and here 30 V2, okay, and the first pressure was 1 atmosphere. No, I'm sorry. 1 over P here. It should be V. V1 equal to V2 equal constant. Okay. If you substitute by 60 here and 30 for the volume and the first pressure 1 atmosphere, you will find the unknown pressure will be 2 atmosphere. Okay, so if you decrease the volume to half, you will find the pressure increases to double. And here the pressure is 1 atmosphere, so the height of the column should be that one, 760 millimeter mercury, which is another atmosphere. So 1 atmosphere plus the other atmosphere, it will be 2 atmosphere. Okay, great. That's great. Okay, this figure shows the relation between the volume and the pressure. If increase the volume, okay, the pressure decreases. Okay, balloon rises up through the atmosphere. Okay, that's great. Okay. Boyle's law states that the volume of a fixed quantity of a gas at a constant temperature is inversely proportional to the pressure. Okay, this is a mathematical expression. You could write it in that way, or you could, if you have different sets of the same gas, P1 V1 equal to P2 V2 equals P3 V3. Okay, till Pn Vn and so on. Okay, this is Boyle's law. Okay, if the relation it's P or V, PV equal to constant. If you draw a diagram or a figure between the pressure and the volume, you will get this curve. Okay, so you could expect that if you plot volume against 1 over B, you will get straight line passes with the origin as you see. Okay, a plot of V versus V result in a curve, but plot V against 1 over B, you will get a straight line. That's great. Okay, let us go to the second law, which discussing the properties of gas. It's called Charles' law, which studies the relation between the volume and the temperature. And the temperature for all gas laws should be absolute temperature, should be Kelvin. Okay, it should be in Kelvin, uppercase T. Once you are studying the volume and temperature, the amount of gas in and the pressure should be constant. Okay, so the volume fixed amount N, okay, at constant pressure, okay, P also constant, is directly proportional to the absolute temperature, okay, as I have already written. So you can remove this sign and change it with equal sign, so it should be constant times T. You can rearrange it, it should be V1 divided by T1, should be constant, so V2, T2, and so on. Okay, as you have seen, when you heat amount of gas, its volume increases, just you cooling it, the volume decreases. Okay, this is the mathematical expression. V equals to constant times T. You could write it in that way. Okay, it could be equal to V2, V1, T1, as I mentioned, V2, T2. If you have two different sets of certain gas at constant amount of gas and the pressure, you can get the other unknown parameter. When you draw a relation between V over T, okay, and the temperature here in Celsius, you will get a straight line, okay, and the extrapolation of this straight line will intersect the temperature axis at the temperature which equal to minus 273, which is 0 Kelvin, which at 0 Kelvin. Okay, a plot of volume versus temperature will be a straight line, as you have seen. When T is measured in Celsius, the intercept on the temperature axis will be that value, we define it as absolute 0 or 0 Kelvin, which equals to that one. And the interconversion between Kelvin and temperature comes from this one. The temperature by Kelvin is given by Celsius plus 273.15, as you know from the previous discussing. The third law is Avogadro's law. Avogadro's law studies the relation between the amount of gas, the volume, and the amount of gas in number of moles at constant pressure and the constant temperature. These are constant, okay? You can change this one with equal sign, should be times constant, or you could write it V1 over N1 equals to V2 over N2, and so on. Okay, the volume of a gas at constant temperature, okay, great, and the constant pressure is directly proportional to the number of moles of a gas. And the mathematical expression, mathematical formula is that one, as I have already written in the front of you. Okay, this figure shows you the relation between the amount of gas and the volume. If you have these three different gases, helium, nitrogen, and the methane, and all of them, okay, the volume of all are 22.4 liter, as you have seen, okay, and the pressure and temperature, these are constant, 1 atmosphere and 0 Celsius, okay. The mass, okay, you will find the mass of this volume, the mass of this volume of helium, it's 4 grams, okay, and the mass of this volume of nitrogen is 28 grams, which is the molar mass of nitrogen, and for methane is 16 grams, which is molar mass of methane, okay. What does it mean? It means that, okay, this, I have already told you before when I was defining the mole, I told you mole that it's just number according to the unit. It could be molar mass, it could be Avogadro's number with 6.02 of molecules, and it could be, when you are talking about gas, it could be 22.4 liter, okay. So we could conclude that 1 mole of any gas at 1 atmosphere and 0 temperature, its a volume, it should be that one, which, okay, 1 mole, which contains the molar mass, which contains Avogadro's number of molecules, its a volume, it will be 22.4 and so on. Okay, that's great. So we can show that, as I mentioned, that 22.4 of any gas, okay, at 0 Celsius contains Avogadro's number, which is 1 mole. Okay, so the 1 mole, the volume of any mole of any gas at 0 Celsius should equal to should equal to 22.4 liter. That's great. Okay, the figure again, like the previous one. Okay, now we have 3 laws of which discussing the relation between the parameter of gases, volume, pressure, temperature, and the amount of gas. We can collect them in one equation, which is called the ideal gas equation. How we can do that? Just be with me. We have seen from Boyle's law, V is inversely proportional to pressure, okay, and according to Charles, volume directly proportional to temperature, and according to Avogadro's, volume directly proportional to the amount. We can collect all these laws in one law, so one could write V is okay proportional to T n directly and inversely to the pressure. So we can remove this sign and put the constant. So it should be V equal to constant. We call it R right now. times T times N divided by P. Just rearrange it, this one, okay, in that place. It will be P V equals to nRT, which is the ideal gas equation or ideal gas law. Okay, where R here is the proportionality constant. It's called the ideal gas constant. Ideal gas constant. Okay, let be with me. Okay, so far we have seen that according to Boyle's inversely proportional to pressure, according to Charles, directly proportional to temperature, according to Avogadro's, directly proportional to the amount of gas. You can collect them in one law as you, okay, and you end up combining them with the ideal gas equation, which is PV equal to nRT, where R is the constant, okay, proportionality constant is R, it's called the ideal gas constant, okay, and it has, okay, it's unit. As I mentioned, to be a good chemist, to be a good scientist, you should be aware with the units. R, okay, you could get its unit from its equation. It should be PV divided by NT. It should be unit of pressure times unit of volume divided by unit of number of mole, which is moles, okay, divided by temperature, which is Kelvin. So you could expect that the unit, it should be unit of volume, liter, pressure divided by mole لكل Kelvin, okay, liter atmosphere per mole per Kelvin, and its value with this unit 0.082, okay. Okay, you can change them according to the units you are using. It could be joule mole لكل Kelvin, and this one is the SI unit. It should be 8.314 joule, okay, divided by mole and Kelvin, okay. It could be unit of volume, which is cubic meter, times unit of pressure, which is Pascal, it's okay, divided by mole لكل Kelvin. And also this one is SI unit, okay, where cubic meter in Pascal, you could conclude that equals to joule. And it could be unit of volume, liter, pressure, torr, divided by molecular Kelvin, it will be this value. So you can choose the unit which in agreement with the something in your hand. So the R, which is gas constant, equals to this value or this value by joule لكل mole or cubic meter, Pascal, and so on. The relationship, I have already derived it in the front of you. Okay, it's R, and you end up with the very, very famous equation for the gas, which I'm sure all of you know this equation. PV equals to nRT. Okay, that's great. Okay. STP, which I mentioned before, it's standard temperature and pressure condition. It means the temperature is 0 Celsius, which equals to 273 Kelvin, and the pressure at that standard condition, it's 1 atmosphere. So the standard temperature is 0 Celsius, and you should be aware that I'm not going to discuss it, to tell you that, okay, in order to not conflict you. Okay. Or okay, STP, the temperature is equal to 273, and the pressure equal to 1 atmosphere. Okay, we can calculate from that equation the volume of 1 mole at STP. Okay, just we substitute for the pressure with 1 atmosphere and temperature was 273, okay, 0.15, and the number of mole just 1, and the R with its value with this units, okay, with this units, with atmosphere, so you end up with the volume in liter. So we can calculate the volume of 1 mole at STP, and it will be that value, okay? So the volume equals to nRT divided by P. Ln, it's 1 mole, okay? R, that value, which liter atmosphere, okay? And temperature is that one, and the pressure is 1 atmosphere. You will find that the volume of 1 mole of gas at STP equal to 0.241, which is Avogadro's law we have discussed before. Ideal gas equation. Okay. We can derive, okay, be with me. We can derive all gas laws we have already derived from the ideal gas equation. Okay. Before that, okay, you have PV equal to nRT. You could write it PV over NT equal to constant R. If you have two different sets of gas, you have a gas with different sets, different pressure, different volume, different temperature, different N, it should be, you could reach to that equation, okay? P1 V1 divided by N1 T1 equals to P2 V2 N2 T2 equals to P3 V3 divided by N3 T3 and so on. Okay? Okay, it's ideal gas equation, that one. By the way, we can derive all equations from this one. Okay, be with me. If you fix number of moles and temperature, N is amount of gas is constant and temperature, you will find that P1 V1 equal to P2 V2, which is Boyle's law, okay? If you fix pressure and temperature, you will find that V1 divided by N1 equal to V2 divided by N2, which is Avogadro's law. Okay, if you fix the pressure and the number of mole, fixed them, you will find that V1 divided by T1 equals to V2 divided by T2, which is Charles' law. Okay, see, you can derive the all gas laws from the ideal gas law. Okay, be with me. Okay, when we were reading that, if PV equals to nRT and N and T are constant, then BV equal to constant. So you can Boyle's law. Other laws can be generated similarly. I have already done in the front of you. In general, if we have the gas under two sets of equation, okay, then we get this relationship, P1 V1 divided by N1 T1 and so on. Great. This is ideal gas equation. Okay, you can calculate any, if you have gas under different sets, you can calculate the unknown. If you fix, for example, you have P and temperature, and volume and N should be constant. So it should be P1 divided by T1 equal to P2 divided by T2. If you substitute the initial pressure 1.5, okay, and the final pressure you don't know, okay, and temperature T1 it should be in Kelvin as I told you, and the second one 723, you can calculate this the unknown parameter. Okay, if you have just only the number of moles constant, should be V1 divided by T1 equals to P2 V2 divided by T2. Okay, just substitute the first pressure 1 atmosphere, second pressure 0.45. Okay, the first volume 6 liter, and the second one is unknown. Temperature should be in Kelvin as I mentioned, 252. You have unknown only that one, you can calculate it. You can calculate the unknown parameter and so on. Okay, now let us discuss the application of ideal gas law. What we can do from that equation, PV equal to nRT. Actually, the first application, you could calculate the density of the gas by the ideal gas equation. How? Okay, I'm going to do it in a way different from that one. Just be with me here. PV equal to nRT. Okay, just number of mole I have told you when we were discussing the N, it's equal to weight divided by molar mass. Okay, so substitute instead of N by that one, and we can make a rearrangement. Okay, just let it do it in two steps. PV equal to weight divided by molar mass RT. Great. Just bring V in this direction under weight and move this to the other one. So we end up with weight divided by volume equals to pressure the same, times molar mass should be divided by RT. Do you remember what does it mean? Weight per volume, it's density. Weight per volume, it's density. So the density equals to pressure divided times the molar mass divided by ideal gas constant times temperature. So you could calculate the density, and also from the same equation you calculate the molar mass. Just if you have the density, molar mass equals to density times RT divided by pressure. Okay, here I'm doing it in a different way, but should be the same. Okay, you end up with the same results. Rearranging the ideal gas equation, N over V equal to P times RT, and then multiply both sides by molar mass. Okay, nothing changed if you multiply both sides. N times M, it's weight. This N number of moles times molar mass, it's weight divided by volume, it's density. It should be that way. P molar mass divided by RT, like I've already showed you. Okay, and you also calculate the molar mass from here. It's density RT divided by pressure. That's great. Okay, that's great. Okay, we can manipulate the density equation to enable us to find the molar mass and so on, as I have already derived you in the front of you in two different ways, and we end up with the same results. Okay. اوكي اتمنى ان انتم ان شاء الله تكونوا معايا. اوكي حلو. اوكي we are 38. That's great. Okay, inshallah I'm going to take the attendance after the next part, which I will finish my lecture with Dalton's law. Okay, if you have Dalton's law, it's dealing with a mixture of gases. If you have a mixture of gases, okay, if you have one gas, when you are talking about its pressure, you call it absolute pressure. If you have a mixture of gases, A plus B plus C gases, okay, so the total pressure of that mixture should be equal to pressure of A plus pressure of B, summation of all pressures you have, of all gases you have. And in that case, we call that the pressure of only A, it's partial pressure of A. It's exactly the same pressure as if it behaves like alone. Okay, be with me. Okay, the total pressure of a mixture of gas equal to the summation of the pressure that it should exert if it were present alone. In other words, the equation I have already showed you, but I have written instead of 1, 2, 3, just A, B, C, and so on. Okay, okay, be with me. Here I'm going to derive the relation between the partial pressure, and very important parameter, which is mole fraction. Do you remember mole fraction? I'm discussing it when we were discussing the units of concentration, I think, and also when we were discussing the mole fraction of component I equals to number of mole of that component divided by the total number of mole, N total. Okay, this small fraction, chi I, xi, it's okay. Okay, how we can derive the relation between the partial pressure of I and xi? Let's see. Okay, P total equals to P1. P1, you could, according to ideal gas equation, equals to BV nRT. You have that mixture in the same container, so the volume the same, temperature are the same, and R are already constant. Okay, R constant. So you could write it P1 V. Okay, sorry, just I'm sorry, just P equals to nRT divided by V. So substitute about HP by that value. Should be N1, okay, times RT divided by volume. These are constant, plus N2 times RT divided by V plus N3 RT divided by V. You can take this as a common factor. You end up with that B total equals to N1 plus N2 plus N3 times RT divided by V. That's great. That's B total. Okay, that's P total. Do you remember this equation? Just write I, as I mentioned, I and VRT are constant. Okay, this equation 1 and this equation 2. Can you divide 1 by 2? You end up with the following. Pressure. Okay, I'm sorry. I'm going to change the color. Okay. Pressure I divided by pressure total. RT will cancel each other. RTV. Okay. I'm sorry. This equation. RTV cancel this equation. This is PI. The remaining one is NI here. Okay, it should be equal to NI. And the remaining part here, it's summation of all N, which is N total. Okay, which is N total. And this one equals to chi I with more fraction of I. So the partial pressure of any gas in a mixture equals to its mole fraction times the total pressure. That's Dalton's law. Okay, be with me. Okay, that's great. P total is given by this one, H gas obeys ideal gas equation, which this one I have already showed you. Okay, and if you substitute in the previous one here, you end up with this one, and these are the summation. N1, N2, N3 are summation, as you see. Okay, and if you divide these two equations together, okay, this one and this one, if you divide them, you end up with that equation I have already showed you. Okay. Hello. Just wait. I will be with you in a few seconds. Okay, be with me. Thank you so much. I haven't finished yet. Okay, that's great. As I told you, it have seen that the partial pressure of any gas, partial pressure and the mole fraction, let n be the number of mole of gas I exerting a partial pressure Pi, then it's given by the mole fraction times the total pressure, where Xi equals to the mole fraction of that component I, which is given by the number of mole of that component divided by the total number of moles. Okay, inshallah, المرة الجاية I will start from the collection of gases over water, inshallah. بإذن الله، وأتمنى إن شاء الله تكون وصلت لكم المعلومة، وأي حاجة just tell me now.